Greetings to all. This is Kavitha, Assistant Professor from PG and Research Department of Mathematics, the Standard Fireworks Rajaratnam College for Women, Sivakasi. In this video, we are going to know about what is a continuous function by analyzing various examples and properties. So, in a layman point of view, a continuous function is nothing but if we are able to draw the graph of the function in a paper without lifting our pen. Right. So, in the first example, we can draw the graph by using a pen without lifting. So, there is no break in the first function. So, it is a continuous function. But in the case of second example, until we are reaching the point 1, 2, we can draw without lifting our pen. So, from 1, 2, we have to lift our pen to 1, 4, then we can continue our function, right. So, at the point 1, we are actually breaking the function. So, this second example is not continuous. So, it is called a discontinuous function at the point 1. So, in a layman point of view, it is simple to define continuous by using a breakage, right. But if we want to define it mathematically, we need some definitions, right. So, epsilon and delta balls are there. So, by using that balls, we are defining what is a continuous functions mathematically and precisely. So, before entering into the definitions of a continuous function, let us define what a limit of a function means. Suppose we are having two metric spaces S and T with matrices ds and dt respectively, and we are having a subset A of a set S and P be a limit point of the set A, and we are having a function f from A to T. Now, the notation limit extends to P f of x equal to B means that for given epsilon greater than 0, we have to find a delta greater than 0 such that if we have a point x in A that satisfying the condition that the distance between the point x and our point P is less than delta and it is greater than 0. So, greater than 0 means the distance between x and P is greater than 0. That means the point x and P are different, right. So, if we are having a point x that satisfy these conditions, then their images, that is f of x and b. So, the distance between f of x and b in the metric dt has to be less than epsilon. If this condition is satisfied, then we can say that our function f of x approaches b if we approach x to the point P. That means we can make f of x arbitrarily close to the point B by sufficiently choosing our x close to the point P. So, next comes the theorem. So, in this theorem, suppose we are having a point P which is the limit point of our set A, and we are having the point B which is in the set T. Then to say limit extends to P f of x equal to B, we can easily say that the limit of f of xn converges to B. That is, if we are having a sequence xn that converges to the point P in the set A difference P, whenever we are having this sequence, then the image of the sequence, that is the f of xn, has to converge to B. So, if this happens for every sequence, then we can say that the f of x approaches B whenever x approaches P. So, here comes the definitions of a continuous function. So, suppose we are having two metric spaces S and T, and we are having a function f from S to T, right. Then f is said to be continuous at a point P in S. If given epsilon greater than 0, we have to find a delta greater than 0 if the distance between x and P is less than delta. If we are having a x with the distance between x and P less than delta, then the distance between f of x and f of P under the metric dt has to be less than epsilon. If this happens for every x satisfying this condition, then our function f is said to be continuous at the point P. If our function f is continuous at every point of S, then our function f is said to be continuous on the whole domain S. So, in this figure, actually we are going to say the function f is continuous at the point x naught, right. So, first what we have to do is first to find the image of the point x naught under the function f, that is first to find f of x naught, right. So, there is a epsilon that is already given to us. So using that epsilon, we are actually drawing a ball around f of x naught. So that ball is nothing but f of x naught minus epsilon comma f of x naught plus epsilon. So by using that epsilon, we are drawing a ball around f of x naught. Now what we have to do is, we have to find a delta in such a way that the interval x naught minus delta and x naught plus delta, that is the ball with the center at x naught and the radius delta, the ball, this ball, and the image of this ball has to be inside the epsilon ball, right. So f of x naught comma minus epsilon comma f of x naught plus epsilon. So if this delta ball, the image of this delta ball lies inside the epsilon ball, then our function is said to be continuous at the point x naught. So this is the definitions of continuous functions in terms of balls. A function f is said to be continuous at the point P if given epsilon greater than 0, we have to find a delta greater than 0 such that the image of the ball with the center P and radius delta has to be inside the image of the ball f of P with radius epsilon, right. So this is the pictorial representation of the above definition. Okay. So if P is a limit point of S, then the definitions of continuity implies that limit extends to P f of x equal to f of P. So these are some remarks. Suppose we have a point P in S which is an isolated point. Isolated point means which is not a limit point, right. Then every function f defined at P will be continuous at P. So if we are having a function that is defined at an isolated point, whatever function it may be, that function has to be continuous at P. This is because if we are choosing delta sufficiently so small so that there is only one x satisfying the distance between x and P is less than delta, that x is nothing but our point P itself, and surely the distance between f of x and f of P is 0 because f of x is nothing but f of P. So the distance between the same points is 0, right. So if we are having a function that is defined at an isolated point, then the function is continuous at that point. So the next remark is, if we are having a function f from S to T, where S and T are two metric spaces and we are having a point P in S, then the function f is continuous at P if and only if every sequence xn that converges to P in S, their images, that is the sequence f of xn is in the codomain, right. So it is in T, that has to converge to the image point f of P. So in symbols we can write the limit n tends to infinity f of xn equals f of limit n tends to infinity xn. So the interchange between the limit and the function is only valid if our function is a continuous function. So this theorem remarked that for continuous functions the limit symbols can be interchanged with the function symbol. So next is some theorems. So in the first theorem we have three metric spaces S, T, U with metrics ds, dt, du respectively, and we are having two functions f from S to T and g from f of S to u, and h is a function that is nothing but the composite of the two functions g and f. If f is continuous at the point P and g is continuous at the point f of P, then our composite function h is continuous at the point P. So this theorem says that the composition of two continuous function is again a continuous function. So next theorem connects the continuity and the open set, right. So if we are having a function f from S to T, where S and T are two metric spaces, then our function f is continuous on S if and only if every open set y in T, right. So in codomain we are having a open set y, then the inverse image, so f inverse of y will be in domain S, right. So if y is open in codomain, then the inverse image f inverse of y is open in domain. Okay. So this theorem says that the inverse image of open set under a continuous map is always open. So similarly, if we are having a closed set in a codomain, say y, then the inverse image f inverse of y is closed in the domain, right. So the inverse image of a closed set under a continuous function is closed in our domain. So in topology we are not at all having a metric structure. we are not at all having a distance structures and all. So the definitions that we have for continuous function in terms of epsilon, delta and in terms of sequence are not valid in a topological spaces. So in topology we are defining a continuous function by using these theorems. A functions in a topological space x to y is said to be continuous if the inverse image of every open set of codomain is open in the domain. Similarly for closed set. So these two theorems actually will be the definition for the topological spaces for continuous functions. So next is an example. Suppose we are having a function f from R to R defined by f of x equal to x sin 1 by x if x is non-zero and 0 if x is 0. So we have to prove this function is continuous at x equal to 0, right. So this, if you are analyzing these functions at the point x equal to 0, at the point 0 the function is splitting, right. So at the point 0 only it takes 0 and all other points it takes the function x sin 1 by x. So other than the point 0 the function f is actually continuous. That is because sin 1 by x, right. So 1 by x is actually a continuous function without 0, right. At the point 0 itself it is not continuous. So other than 0 1 by x is continuous. And sin x, so sin x is a trigonometric function, so it is also a continuous function. So sin 1 by x is nothing but the composition of two function sin and 1 by x. So composition of two continuous function is always continuous. So sin 1 by x is a continuous function. X into sin 1 by x. So we are taking the product of two continuous function, right. So that is also continuous, right. So product of two continuous functions is continuous. By using this result, sin 1 by x is actually a continuous function in the domain R difference 0, right. So surely x sin 1 by x is continuous in R difference 0. So then what about 0? So to prove f is continuous at this point 0, what we have to prove is limit x tends to 0 f of x equal to f of 0. So we have to approach 0 in the domain so that the image f of x has to approach f of 0. So limit x tends to 0 f of x equal to limit x tends to 0 x sin 1 by x. Here x sin 1 by x is a bounded function and x, if we approach x to 0 then x also approaches to 0. So we are having a sequence that approaches to 0 and another sequence that is a bounded. So if we take the product of these two then our final sequence has to converge to 0. Thus the limit x tends to 0 f of x equal to 0. Also f of 0 is 0. From the function itself we can say f of 0 is 0. Thus the limit x tends to 0 f of x equal to f of 0. Thus our function f is continuous at the point x equal to 0. If we are analyzing this function graphically, this is the graph of the function, right. So at the point 0 our function value is 0 and if we are approaching the point 0 in the domain from right hand side then also this graph will converges to the image 0. If we approach the point 0 in the domain from the left hand side also then the graph converges to the point 0. Thus from the figure itself we can say that the function is continuous at 0. Here comes the second example. In the second example we have a function f from R to R defined by f of x equal to modulus of x plus greatest integer function. This function what we have to prove is this function is discontinuous at x equal to 0. This greatest integer function is a function that takes the value, if we are taking the value of greatest integer function of 0.5 then it is 0. If we are taking the value of 1.5 then it takes the value 1. So it is the largest integer that is less than our point x, right. So now to prove this function is not continuous at the point 0, what we are going to do is we are going to take the limit of the function that 0 from left side and right side. So limit x tends to 0, 0 minus f of x. So if we are approaching 0 from left side, right, then mod of x is actually 0 and if we are approaching 0 from left side then the integral part is negative, right. So the integral part of minus 0.5, minus 0.3 all are minus 1. So 0 plus minus 1 is minus 1. So what we have is the left hand limit is minus 1. So if we are approaching 0 from the right hand side then the mod x is always 0 and the integral greatest integer function of 0.5, 0.3, 0.2 all are 0, right. So the right hand limit is 0 plus 0, that is 0. So the left hand limit is minus 1 and the right hand limit is 0. So the limit itself, the limit of the function itself is not existing, right. So the function is not continuous at the point x equal to 0. So here comes some properties of a continuous function. Suppose we are having two functions f and g that are continuous at the point alpha, then the linear combinations of f and g is also continuous at alpha. The linear combination means a into f plus b into g is also continuous at alpha, where a and b are some constants. And the second property is the product of two continuous function is continuous at the point alpha, that is f into g is a continuous function at alpha. The third property is if we are taking the quotient of two continuous function, f difference f by g is also continuous at x equal to alpha. We are taking the quotient, right. So our denominator has to be not 0. So g of alpha has to be not equal to 0. And the fourth property is if we are having a continuous function and if we are taking the modulus of that function, then that function is also continuous at the point x equal to alpha. So modulus of any continuous function is continuous. And the fifth property is if we are having two continuous function f and g and if we are taking the maximum of these two functions, then the resulting function is also a continuous function. This is because the maximum of f comma g is nothing but f plus g plus modulus of f minus g by 2. So f is a continuous function, g is a continuous function. By property 1, f plus g is a continuous function, f minus g is also a continuous function. And by property 4, modulus of f minus g is a continuous function, right. Again by property 1, sum of two continuous function is continuous functions and the average of a continuous function is a continuous function. Thus the maximum of f and g is a continuous function at the point x equal to alpha. Similarly for the minimum, so minimum of f comma g is also be defined as f plus g minus modulus of f minus g by 2. So again by using the same logic we can prove that the minimum of two continuous function is also a continuous function. So these are some of the important properties that we have that connecting the continuity, right. Okay. So the concept of continuity is very much important in fields such as physics, economics, modeling, etc. And it is very much used to model various situations. So understanding the concepts of continuity and the properties and its behaviors is very much essential. Thank you one and all.